Okay, so yeah, this is joint work with Ron Siegel. We're both at Penn State. And the starting observation of this paper is the point that with the growth of information and communication technologies, firms have access more than ever before to detailed consumer data, such as their age, sex, location, or browsing history. They can segment the market based on these observable characteristics and make personalized offers to each consumer segment. A natural question that arises is, what is the effect of this segmentation on consumers? On one hand, we know that segmentation can harm consumers. If the seller can perfectly distinguish each individual buyer, they can ask them to pay what they're willing to pay for products and extract all the surplus. The question we're asking is, can segmentation benefit consumers? For motivation, imagine a social planner, like a government regulator, who can choose the segmentation by telling the firm which characteristics it can price discriminate upon. So you're allowed to price discriminate based on sex, but not, say, age. And the question is how to choose these characteristics. As an example, consider a population of consumers, like everybody in the United States, who are served by a multi-product monopolist who would sell the products by offering a menu from which each consumer will make a choice. So each consumer is going to have some utility or some surplus, which is the difference between how much they're willing to pay for their favorite product minus how much they actually do pay. Let's call that utility of consumer C for every single consumer C. Now we can ask, what if the market is segmented? A segmentation is simply a partitioning of this distribution into individual, what we call segments. Now the seller is allowed to offer a different menu to each segment. And therefore, its consumer C is going to be able to choose from a different menu. So this consumer C can only choose from menu 1. The utility of the consumer depends on the options available, which itself depends on the menus that the seller decides to offer to the consumers given the segmentation. So the utility now depends on how the market is segmented. The question is, does there exist a segmentation that benefits consumers in a very strong sense, namely Pareto? That every single consumer is weakly better off with the segmentation than without, and some consumer C strictly benefits from the segmentation. We call this a Pareto improving segmentation of the distribution. Let me give you some examples. Let's say this firm is selling a single product that can produce at 0 cost. A Q fraction of consumers have value 2, 1 minus Q have value 1. I'm going to show that a Pareto improving segmentation exists if and only if Q is between 1/2 and 1. So the fraction of the high types is more than 1/2. For simplicity, let's just say that Q, the fraction of the high types, is 2/3. What would the seller do if the distribution is not segmented? Well, it would offer the high price because the proportion of the high types is more than the low types. The price would be 2. Every single consumer will get a utility of 0. Now I'm going to give you a segmentation which only basically consists of 2 segments. So put all of your low-value consumers together with half of your high-value consumers in one segment. Let's call that the north segment. The remaining high-value consumers will go to the south segment. What would happen now? The seller in the north segment sees a half-half distribution of consumers. It would be optimal to sell the product at price 1. Every single consumer, well, the consumers of value 2 in the north segment get utility of 1 because now the price is 1, they're willing to pay 2. The consumers in the south segment don't notice any change because their utility would be 0. Now notice that every single consumer has weakly high utility with segmentation, and some consumers, namely the ones that end up being in the north segment and have high values, are strictly better off with this segmentation. Why is this not possible if Q is less than 1/2? Well, if Q is less than 1/2, in the unsegmented distribution, the seller will already offer the lowest possible price, which is 1. There's no way to give consumers more utility than that. And this is general observation. If you have any distribution over values, such that the seller finds it optimal to post the lowest value as a price, there is no Pareto improving segmentation. So the real interesting question is, what happens if the allocation is not efficient, if the seller is posting other prices? And in fact, Bergman, Brooks, and Morris show, among many other results, that Pareto improving segmentations do exist when you're selling a single product. So the question you're asking is, what about multi-product markets? Now I'm going to show you an example with multiple products where there is an inefficient allocation and no Pareto improving segmentation exists. That would be a sharp contrast with a single product case. So say there are two quality products, low and high. Still a Q fraction have high types, 1 minus Q low types. Value of the high types is 1 and 2 for low and high quality. The value of the low types are 0.75 and 1 for low and high quality. If the proportion of the high types is 0.75, there exists no Pareto improving segmentation, even though the allocation is inefficient. That's what I'm going to show you now. So what would the seller do in this case if the distribution is not segmented? It would offer a menu, low quality product at price of 0.75, high quality product at price of 1.75. Utilities would be 0 and 0.25 for low and high types. Now I'm going to argue that there exists no Pareto improving segmentation. How do you show that? The point is that no matter how you segment the market, there is going to be some segment in which the proportion of the high types is going to be strictly more than 0.75. Otherwise, your segmentation is trivial. In that segment, the seller will end up giving lower utility to consumers of high types. So let's say that this is a segmentation, and the middle segment is the one in which the fraction of the high types is more than 0.75. The optimal mechanism for that segment would be to only sell the high quality product at price 2 and give everybody, including the high types, utility 0. So some consumers, namely type 2 consumers that end up in a segment with more than 0.75 proportion of the high types, end up being hurt. What we show in this paper is such examples are in fact non-generic. For almost but a finitely many number of distributions, Pareto improving segmentations exist. This is for the case of 2 types, as in this example. And we have a generalization to any number of types that I'm going to tell you after I tell you what the model is. Here's a model. There's a finite number of types, 1 to n. There is a finite number of items, 1 to m. The utility or the valuation of type T for item I is Ti. There can be costs. I'm going to assume that there is 0 in this talk. A mechanism is a randomized mapping from a type to distribution over items and a payment for each type. IC and IR are defined as usual. Now you can define for every type T in every distribution F a utility of that type in the optimal mechanism for distribution F. This would be the utility that type T gets if the distribution is not segmented. Now we want to compare this utility to the utility that the type gets in the segmented distribution. So what is a segmentation? Segmentation is simply a distribution over segments. So a distribution over types. The only constraint is that there is a base plausibility constraint, or the fact that a segmentation preserves the proportion of the types, meaning for every single type, if you add up the fraction of these type in every single segment, they have to add up to the proportion of that type in the unsegmented distribution. That's what this constraint is saying. We can now say what a Pareto improving segmentation means. That means, as I just said before, every type in every segment has weakly higher utility than they do in the unsegmented distribution. Some type in some segment strictly benefits. And the question was, for what distributions F, Pareto improving segmentations exists? Here is the answer. Before I tell you the answer, let's remind ourselves that I said if allocation for a distribution is efficient, there is no scope for improvement because there's nothing else you can do with segmentation. Efficient in this case means that every single type gets the best product among all the items. So the question was, what about inefficient distributions? And the theorem says that for almost all inefficient distributions, Pareto improving segmentations exist. What does almost all mean? It means that the ones that are the inefficient distributions for which Pareto improving segmentations do not exist are small or non-generic in the sense that they can be contained in a finite union of lower dimensional hyperplanes. Let me show that with a picture. Let's consider the set of all inefficient distributions. Let's consider the intersection of that with a finite number of hyperplanes. In this case, would be a finite number of lines. The intersection would be the red solid set. The set of inefficient distributions for which Pareto improving segmentations do not exist is contained in the red set. Everything else is a set of inefficient markets for which Pareto improving segmentations do exist. A special case is what I just said for the two types, which says that the number of inefficient markets for which Pareto improving segmentations do not exist is finite. So for the rest of the talk, I will walk you over the proof. It consists of two steps. And in fact, before I tell you that, the segmentation that we construct for our possibility result simply consists of two segments. So we say that whenever we construct such segmentation, it only has two segments. Good. So here's the outline. Give me any inefficient distribution F. The first step is to show that every such distribution is dominated by some other distribution F1. What does dominated mean? It means that every type in the support of F1 has weakly higher utility than they do in F, and some type in the support of F1 has strictly higher utility than they do in F. This is a general statement about a general mechanism design setting. It's not about segmentations or anything. It just says that give me any distribution. If it's not efficient, there exists another distribution in which types have higher utility. And this is, in fact, the core of the proof. So I'm going to spend some time on it later. The second step would be to, now that we know such a distribution exists, to construct a segmentation. The segmentation is very simple. It basically says that put a very small fraction of the consumers in this market F1, in this distribution F1 that we just constructed, put everybody else in what we would call F2. So this constraint just does the base plausibility constraint that says that you can put an epsilon fraction in F1, everybody else in F2. So now notice that we already argued that every consumer in F1 weakly benefits and some consumers strictly benefit. So all you have to make sure is that nobody in F2 is hurt from segmentation. The way to do this is to say that, well, if epsilon is very, very small, F2 becomes essentially the same as F. So you have two distributions that are getting closer and closer to each other. Then you just need to argue that the optimal mechanisms become the same as well if distributions are close enough for generic, for almost all distributions F. This holds even though the number of possible mechanisms is infinite because we allow for randomized mechanisms. So I'm going to now go over each step one by one. The first step, as I said, is that if you have a distribution in which the allocation is not efficient, there exists another distribution in which types have higher utilities. Notice what this is not saying is that it's not just saying that there exists another way, another mechanism that gives types higher utility. Of course, you can do that by paying money to types. It is saying that there is another distribution in which it is optimal for the seller to give types higher utility. So I'm going to go over the proof. This itself consists of 3 steps, and it does not need any assumptions. I'm going to prove it to you with some assumptions for simplicity today. One is that there exists a best item, an item that everybody likes more than every other item. So if you project the values, it's going to be below the 45-degree line. The second assumption is that there exists a lowest type, a type that has higher value than any other type does for any item. That would be this type, T lower bar. So there's going to be 3 steps. One is that in the optimal mechanism for distribution F, the best item should be sold to somebody. If you're not selling the best item, you can offer it at a high price and improve revenue. That would be step 1. Step 2 would be the price of the best item must be strictly higher than what the lowest type is willing to pay for the best item. Again, if you're offering it at a price lower than that, then you're giving everybody, including the lowest type, positive utility, and your mechanism cannot be optimal. So now we know that some type T is buying the best product and is paying strictly more than what the lowest type is willing to pay for the best product. Now we can construct our dominating distribution. That would consist only of 2 types, the lowest type and this type T. Type T is going to have very low probability delta. All the other types in that distribution are going to be the lowest type. So the point is that if delta is small enough, almost all the types are the lowest type, the seller will try to extract the full surplus from the lowest type by offering the best alternative at their willingness to pay, T lower bar of I. Now, type T is strictly benefiting from this distribution because now it has access to the same product it was buying before at a lower price. The lowest type is not harmed because the lowest type gets utility 0 in any distribution. So now we have found a dominating distribution. So let me just briefly go over the second step as well. The point was to show that if 2 distributions are close to each other, then the optimal mechanisms become the same for close enough distributions. The point is to show that the set of all IR and IC mechanisms is a polytope defined by a finite number of constraints. The set of payments is a projection of that polytope and therefore a polytope itself. The optimal mechanism design problem would be given a direction, how far can you go among all the possible payment rules, right? And the point is that for almost all directions F, the optimizer would be a unique vertex at this polytope. And if you perturb the direction slightly, the optimal mechanism is not going to change because you're at the vertex. For non-generic cases would be when you're on one of the faces, and there a small perturbation may change the optimal mechanism. To conclude, what we showed is that Pareto improving segmentations exist for almost all distributions, even though they don't always exist. I showed you an example in which they don't exist. The key idea was that every inefficient distribution is dominated. And notice that we have been assuming that all segmentations are possible. So you have a very powerful regulator who can choose every possible segmentation. In reality, this of course doesn't hold because of maybe technological reasons. You cannot perfectly distinguish between consumers. But what this paper is saying that at least there is scope for intervention by the government, for example, by allowing firms to observe some characteristics but not others. Now we can look at specific scenarios and discuss whether or not reasonable ones exist. There is a second half to this paper that I didn't talk about, in which we ask how large can this improvement be given that we know they generically exist. And there we are asking about average consumer surplus instead of Pareto. If you are interested, I can tell you about it offline. Thanks. Yes?
For the second lemma, do you need the support to be discrete?
The finite number of types.
Yes.
Yes.
Oh, okay.
Yes, we need finite number of types and finite number of items. That is crucial, in fact.
Do you allow randomized mechanisms?
Yes, we do allow randomized mechanisms, but as long as the set of types and items is finite, then everything goes through.
If you do this repeatedly, are you likely to end up at an optimal distribution in the end or not? Or is guidance?
Good, excellent. So what this is saying is that if you do this repeatedly, you're going to have to end up in a segmentation in which every single segment is efficient. Because if it's not efficient, then you can keep doing it and improve consumer service.
But couldn't you end up at some degenerate?
Good, except for degenerate cases. I'm sorry, I take that back. So
Maybe like somehow mathematically you would actually end up at a degenerate case. I don't know.
it may end up in a degenerate. Yeah, I actually don't know. That's a good question. Yeah.
And for the proof outline, you broke it into 2 steps. The issue with the proof breaks for a single item because of the second step, or even the first step doesn't hold for
The proof doesn't break for the single item. The theorem holds for a single item. You can even say something stronger. In fact, for a single item, for all distributions, the Pareto improving segmentation exists.
So good
Good. No, we haven't thought about a multi-product case with item pricing. The single product case, of course, any mechanism is item pricing, but we haven't thought about multi-product case with item pricing. No.
Thank you so much.